Here we go. Now, ladies and gentlemen, you can close this model. We will bid it adieu, or at least a goodbye for now. Okay. Great. There we go. Okay. Okay. So it's closed. I would like you now to do something we haven't much done, which is go to Help, and I'd like you to go to Example Models, ladies and gentlemen. Example Models, okay? Now, in Example Models, if you scroll down on the right-hand side, there's many models here, okay? And some of those are models we've contributed. Others are models that AnyLogic has come up with. Some of them are very thought-provoking, and some of them are very interesting. I'd like you to go to SAR agent-based calibration. Okay?
I'm sorry if I go for a minute. How do you scroll down example models?
Sure. I went to Help. Not a problem. Example Models, and we scrolled down on the right-hand side, and we went to SAR agent-based calibration. Are we okay with that? Okay, and then I clicked on that, and it loaded it in.
You can actually do a search there, Nate.
Can you?
Yeah, it looks like a new feature.
What is that?
So if you go Help Example Models.
Okay. Alan told me that your generation
Right there.
doesn't use. Oh, nice.
If you type in the word calibration, you'll get the model.
Nice.
Yeah.
Okay.
Healthcare right there.
Okay, that's really nice. No, Alan told me that his generation no longer says sweet. What's that?
That's more mine.
That's more your generation?
My children's generation says
Sick, yeah.
Yeah,
Not seek.
that's what he told me. Which I found.
Dude, that's totally sick.
It's confusing though whether they actually mean like cool or like bad.
Yeah.
It always means
No,
cool.
it always
It doesn't mean bad ever. Sick does not mean
Yeah,
bad.
that's sick.
Yeah, no, it's true.
Yeah.
That's not good.
No,
You're-
it looks sick.
Sorry,
Is that
but
not
you're not quite that young now.
I know.
Okay.
The other one,
Sick is always a cool thing.
When I was young, the thing that used to be good but it's kind of bad is Wicked.
Yeah.
Right? Which is also kind of bad. Like Wicked is like what like an evil witch does, the Wicked Witch. But like it's a good thing, dude. That's Wicked.
It was always a cool thing.
Huh?
I think that's like where sick comes from.
Okay.
I get the
That's where I'm trying
Okay.
It's
So.
all being recorded for posterity.
Yeah. Okay. Okay. So so ladies and gentlemen, what we'd like to do is to go to this model, and I'm going to run this model, and I think sometimes a picture is worth 1,000 words. So this is going to represent some data that we're going to try to match. Okay. This is some empirical. So the deal here. Gosh, I stand or even sit remiss.
way too cool for me.
Okay. Ladies and gentlemen, we're going to talk just a moment about calibration. The fact is that sometimes we have data about the world. Often we have data about the world that is not about any one parameter in isolation. It's about emergent patterns in the world. And by their nature, emergent patterns can typically not be reduced to just one parameter. They're an entangling of many parameters. But often these patterns are things that we wish our model to stay, to which we wish our model to stay true. That it should, for face validity, it should have some consistency with these patterns. At least it should have some face plausibility in light of these patterns. And if we're going to show our model to policymakers, they may look at the outcomes of our model, and if if it doesn't align with certain empirical data, they may say, well, how do you have any confidence about your model? Now, it's a tricky issue because model, for several reasons. The one thing is that data itself doesn't come from heaven. And I can't tell you the number of times in my modeling career, it's been about 4 or 5, where I've struggled and struggled and struggled because a model doesn't match the data. And it turns out it's because the data had a major problem in it. And I only found that out because of because I tried to match the model against the data. Now, we try to build models, ladies and gentlemen, to deal with counterfactuals. And there is some question of, well, wait a minute, if you're seeking to use this model to examine counterfactual situations where the data generating process is so different, why are you going to spend all this time trying to calibrate it to existing data? And I view it as a matter, opinions differ than this, but as a modeler, if I'm building an empirically grounded model, I want to have some confidence in the model before I start using it to look at counterfactual situations. I want to have some degree of confidence that it's representative of the epidemiological context I'm dealing with, that it has some correspondence to reality rather than just being a neat little plaything. And so I often use calibration as kind of a validation exercise. And sometimes there's especially rigorous forms of calibration where you build the model, calibrate it with a subset of the data, and then test it to see if it then reproduces another set of data that wasn't used in calibration, wasn't used to build it, but you evaluate it against this alternative type of data. And that form of calibration is common in machine learning, and you'll find written about n-fold cross-validation, and you'll sometimes see it in modeling as a good practice, and, to test the predictive validity of the model. But it is true that sometimes we can get great insights from a model into counterfactuals. Even in the absence of really good data, we can get some fundamental insights, even though the particular precise values coming out of it may not be all that accurate. The overall form of the output may be accurate. Calibration can go on at several different levels. Sometimes we calibrate against quantitative estimates that are very precise, and other times we just seek the model to capture the phenomenology of the situation. And Volker Grimm in the Pages of Science has talked about pattern-oriented modeling, where you want your model to capture the qualitative patterns you see in the world without always trying to match the exact details. Think about a physicist, modeling the behavior of a fluid, and they're not trying to exactly match the timing of each wave in the fluid, but they're trying to capture how it responds under different conditions, how it sloshes around in a more qualitative way. So calibration, I don't want you to leave the room and think that every model needs to be calibrated to be valid, or to be useful, I should say. I don't want you to think either that all calibration is necessarily purely against data points. But often we do have data points for empirically grounded models. Often we have data points which go beyond parameter values that we have, which we may base on the literature or primary data or other sources of data, such as from meta-analyses, etc. And we try to use calibration to fill in the gaps in our model estimates. So the idea here is that we have some data from the world, maybe about many different things, and we try to simultaneously have the model during the historic period match those data sources so that then we can with confidence think, okay, this is capturing the basic features of the situation, so we can look forward from there into a counterfactual regime. Situation where we don't have data. We can ask about future, projections forward or future intervention regimes where there's no direct data available. So it's a matter of, to some degree, building confidence in the model. And the point is the model's often trying to match many sources of data. This is an example of a model where we have data on diabetes, different aspects of diabetes, including prevalence and incidence, and ESRD, prevalence and incidence, and death, and type 2 diabetes death. And we were trying to have the model shown here in red and shown here in gray simultaneously match all these time series to develop confidence that it was capturing the essential regularities. And you'll notice it's not perfect. These time series are jumping around. There's stochastic variability because of small numbers. You look at ESRD prevalence and you're getting some small numbers, etc. But the model is capturing pretty well the broad trends here in the data, and highlighted for us some areas where the model might be off.
You don't then have to
Yeah.
validate on some other data set, because you can always create a model to match something.
That's true. Yeah.
So just because you've created the model to match historical data doesn't actually give you any indication that it will be useful in the future.
This is.
Because you could have set, because you've adjusted the parameters to match something, but it could be the completely wrong parameters. You need
It is possible, and this gets into the issues that I'll be talking about with calibration, that how underdetermined or overdetermined is it in terms of the calibration? Because sometimes there might be multiple sets of parameters that match the data, and some of them match well with these parameter values. Sometimes it matches well with these ones, and you're not sure which of them really obtain. But in other cases, it is actually quite it's quite overdetermined. So in other words, or completely determined. So it's you match it, and it's got a unique set of parameters that seem to do the job. But you're right that just because a model calibrates doesn't mean the model is correct. It just at least means it isn't obviously problematic. But it doesn't yet mean that it's correct. And there's often further tests that we'll do, including unit consistency, for example, testing against the results of interventions that are tried out to develop confidence. Remember, models are thinking tools, and they help us think more consistently through the implications of our assumptions. But just because we see a consistency in terms of these data between the model and these particular observables doesn't mean the situation is done. It just means, okay, we haven't yet ruled it out, but we need to develop confidence on an ongoing basis and identify when the model has not captured things, learn from that so we can build a better model.
I just thought you were supposed to
Yeah.
calibrate on one data set and then
No.
verify on another data set.
Oh, no, you can divide your data into pieces like that.
But you need to calibrate on one data set and verify on another data set.
Yeah, that's the cross-calibration idea, the cross-validation idea. So you calibrate on one data set and you test it on another.
That's what you talked about, the n-fold cross-validation.
Yeah,
Just
that's
a
right.
single data set that's being broken up.
That's true. That's true. And that's a weaker form than doing on totally different data sets.
Sure.
Yes. And the reason is because there may be correlation between those data sets. Yeah. You wouldn't want to take every other point of this data set, calibrate it on that, and then test it against the other points, because they're so highly correlated that it's not going to be a really full calibration. So in calibration, basically what's going to happen is it's going to try to leverage this data that we have to try to pin down the values of less well-known parameters. And the typical way it works is by using a global optimization algorithm that adjusts the unknown or less well-known parameters so that the model matches a set of data. And that other data, which is often in the form of time series, although it needn't always be, basically is used to determine the so-called objective function. So the idea is that the parameters of the model that are less well known are being adjusted to minimize the discrepancy between model results on the one hand and empirical data on the other. So it's adjusting these parameters to try to best align the model results with this other data. Now, it's not always the case. In fact, I think it's often not the case that the most valuable thing that comes out of this is the missing parameter values. That's what people think about with calibration. Oh, you're trying to get out the missing parameter values. Often the real important thing that comes out of it is insights, because you find the model cannot match these things. It's not like trying to match a best match and a polynomial of order n against some data where you're going to find some good match and it's going to be overfit. Often what you'll find is that no matter what you do, the model will not match these sort of data, and that's an opportunity for learning. It's not that the model's broken and therefore you have to start again and go home and cry. It's in fact it's a matter of learning about the system. It's a matter of what can we learn about the inconsistencies of how we think about the world and what the data is telling us, or learn about problems with the data. And often we learn something we just would not have learned without the calibration. Even if the calibration ends up being systematically off in several ways, the chances are we have something important to learn from it. It's not a matter of crystal ball is broken. It's a matter instead that we've identified a learning opportunity, and we can try to learn from it to incorporate a better thinking on our part about how things work. And often it's calibration that has alerted me to bad data. I would not have known about this data, except I have to go to the stakeholder and say, the model will not match these time series for these time periods. Why not? What is going on there? What in the world is going on in those time periods? What am I missing in the model? And the stakeholder will often say, well, for those years, the data is unreliable, or we switched the definition as of this year for what was collected, or we had much smaller sample sizes or whatever. And that's learning that wouldn't have gone on without the calibration. Or I'll end up discovering that really to account for the data, I need to disaggregate active TB cases into infectious active TB and non-infectious active TB to really account for the structure of the empirical data that I see in the time series. And that's a point of learning as well. Helps refine my thinking. It just doesn't account for what I see from the world without that. And so this is one of the reasons I said that models are tools to help us make more full use of empirical data. That data was there before, but until I had a model, I didn't understand the significance of it for my thinking. It's only because I tested my thinking in the form of a computational model against the data, that's when I had the insights that I need to refine my thinking. Okay, so calibration is running this optimization algorithm, tweaking parameters and trying to match the data. And it should not be viewed as simply a mechanical process. It's a learning process. So what's required for calibration? A specification of what you want to match, a statement of what parameters you want to vary and over what range to vary them, and some specification of the desired optimization algorithm. So the idea here is we have several parameters. Here I've shown 3, and we're adjusting those parameters. Just like that. And as you're adjusting it, you're trying to find, within the assumptions about beta, mu, and tau, what values of them will offer the best match against the data. Now, I was talking earlier with Joanna. We do a lot of work these days with Bayesian Markov chain Monte Carlo techniques, which actually sample from posterior distributions of parameters, and I'm not going to go into that now, but you'll find videos of me talking about it online, and it's actually a quite hot topic, and it puts really dynamic models to very good use, very powerful use. I'm not going to go into that here, but you could think of it as kind of a generalization of calibration that accounts for uncertainty in a much more rigorous way. So how do you assess model goodness of fit? How do you assess for each of these points how well the model matches the empirical data? Well, there's several measures, but often they involve some sort of discrepancy measure, like a sum square of errors against the data. So you judge the distance, as it were, from the model and the data. And I've written about what sort of good metrics are, etc. And often you're trying to match multiple types of data, so you want it to be a dimensionless metric. So if you have some discrepancy with respect to deaths, and you have some discrepancy, the number of deaths over time, and some discrepancy with respect to the number of incident cases over time, and some discrepancy with respect to the costs over time, you can sort of add up those discrepancies into each other because they're rendered into dimensionless fashion with, the thing over the thing, so this is historic, this is model result, and this is the average of historic model result. If we put this over this, we get a quantity that's a fraction. And because of that, it's dimensionless. We can square it and add it to discrepancies from other things. I'm not going to go into that. But what I do want to show you is for any logic, how this works. Okay? So let's go back to any logic. And here's some empirical data we want to match. Now, I have for my students, I have a generalization of this which matches 2 time series. And I would be glad, as long as you don't send it to my undergraduates or prospective undergraduates, to share with you that model, which has multiple time series that they have to match. That's one of the challenge exercises that I would provide. So here we go. This is empirical data we want to match. We want to match this model's results. Now this model, in any logic, is a model of SIR-based infection spread. So here we go. Go look at person, and there you recognize this general feature. So here we send messages over the network to, and in fact, this is sending it to a random person in the network. So it's random mixing it to anyone, not just neighbors. So here it's adjusting model assumptions about parameters. These are the assumptions. And it's trying to find model parameters that offer the greatest fit to this, the best fit to this historic data. And one of the things that makes it challenging is that for a given value of parameters, it's going to have different results. Why? Because of stochastics, the variability. So it may have a certain set of parameter values, but for those parameters, depending on the vagaries of random numbers, it may run it again and again and again and actually get different results. So what this graph over here is showing sort of the best match yet. And you can see it's homing in. It's honing down its estimate, okay? And you could see some of the estimates yield a big discrepancy. That's what this is showing. But others yield smaller discrepancies in its learning as it tries from different parameter values. It's learning which values work better. And it's finding better and better matches. And for each of those matches, it's running it many times. You could see here it's found a pretty good match for those parameter values. So if we go look at how this parameter variation experiment works, you could find it's running several replications, 5 of them. So for each set of parameter values, it's actually running the model 5 times over. Because it doesn't want to just say, oh, this is a great set of parameters based on one run, and it turns out to be a fluke. It's just a lucky run. Whereas another one it judges as bad because of luck. So, ladies and gentlemen, we want to learn how this is working. So, in this model, it's try and match as well as possible this historic data. How does that actually work? Let's check it out. Okay. So here we are. We're going to go down to the calibration experiment. And if you go into the calibration experiment, scroll up to the top, you'll find a couple things of note, okay? So one thing is you will find a specification of the objective function. And this is in my slides, which I will share with you, okay? It states how many iterations it's going to run, how long it's going to go. Of course, for each iteration, it's going to run it 5 times over. Here, it's asking, how do I compute the discrepancy between the sort of the badness of the match between the historic data and the data from the model, the data output from the model, okay? That's for each realization of the model. Not only is it saying that, it's actually saying which parameters should I vary and over what ranges should I vary them, okay? In this case, it varies this in a continuous way between 0.5 and 5, and this one between 0.1 and 0.8. Okay, and so it's varying these. And there's this automatic stop where it can stop once it has a certain level of precision in estimating the parameter values. Now, AnyLogic provides some mechanisms for easily computing discrepancy functions of stock types. And In this case, it's doing some sort of clear mean squared error. Difference, which is always non-negative, reflects the difference in two data sets. It's the square root of the average of squared distances between linearly interpolated data sets. Okay, so it's a mean squared error type of thing. Okay, and that's what they're using here with difference. Okay, this difference, it takes the difference of two data sets. Notice when I call this up, it says ... in AnyLogic. That's an indication that there's many things called that. If you want to explore it, you press enter. And then it will tell you two of them. Here's comparing one data set to another. And this is comparing a data set to a table function. Okay? Okay, ladies and gentlemen, let's continue on here. We can create our custom difference function if we want, create our own. And this shows one way to do that. Okay, now we can capture historic data in a table function. We've seen table functions before. Do you remember them? We saw them to encode like the fertility rate by age, for example. And data sets can be defined for historic data. And in this case, they take that historic data and they fill it into a data set, okay, which allows you to then use that data set from now on. So they take that data set, this data, and they put it into the data set. Okay, now agent-based models typically exhibit stochastics. Not always, but typically. There are some, like the game of life is, Conway's game of life is a deterministic one, but normally they're stochastic. And so when calibrating an ABM, we really need to deal with those stochastics. And here, AnyLogic makes this distinction between the experiments, which is the whole calibration experiment, a simulation, which is a given replication for particular parameter values and particular values of the parameters, and a replication with a particular run. So actually, we have to be cautious here. This is called a scenario is called an iteration with a particular set of parameter values. So here, what they're doing is quite similar to what we did with the in the case of the parameter variation experiment. So ladies and gentlemen, after each run of a particular realization, we're going to suck out of, do you remember this root.infectiousds? What is root? That's main. So we're going to read out of it this data set called infectious DS. And if we go to main, we'll find there's this data set, infectious DS. And that data set, if we go look at it, it updates data automatically. It reads in the number of infectious people at that time every 2 days. Okay? So having compiled that, when we run main over the course of the run, it is then at the end of that run, it's going to suck that out and it's going to put it into this DS infectious current, which is a data set living here in the calibration. So it's going to suck it out of main because main is about to disappear, and it's going to put it into this one here, DS infectious current. That's the kind of current one. It's going to, oops, no, I don't want to do that. It's going to put it into there. It's going to read it out, and then it's going to use that in order to judge how good it is. That DS infectious current is going to be used to compare with the historic data. Okay, so it's going to compare what we read out of from the model with what historically was the case. And by comparing that, that's going to be used to determine the objective function. And that's all visible here if you scroll around. DS infectious current, that's what we read out down here in advanced Java. Oh, sorry, in Java actions here.
So is it a real, in a mathematical terms, is it a real optimization in that it's determining where it goes based on its
Yes.
history? It's
Yes.
not, it's not just a
No, it's a real optimization. In fact, it's based on a quite popular platform that's available. It's a third-party platform called OptQuest, and it's fairly widely published. This OptQuest engine, sold by a third party. It's an optimization engine. So it's used by Arena, for those whom that's meaningful. That's a very popular and traditionally market dominating over many years a discrete event package. And OptQuest, AnyLogic builds atop the OptQuest engine. It's also an engine that's been used that has been used in many other packages like Simio, Simulate. It seems to be a very popular package for doing optimization in simulation. Okay, so here we do. After each one, we suck that into DS infectious current. That provides the basis for us to determine the objective function. And it actually uses, as I understand it, what's called a genetic programming or genetic algorithm to basically figure out where to go next in a clever way as a global optimization. And
Most of them are only, pretty mindful of local minimum.
yeah, exactly. I think with that, they try to avoid gradient descent and just getting down and getting stuck in a local minimum, but instead try to have some intelligence between exploitation and exploration. So, if you've been here for a while and you're kind of not making any progress, you'll go over a little bit and you find, oh, I can get even lower values by jumping down, and then it will explore a bit more and then go down further. So it tries to be pretty intelligent with that. And it's more intelligent than some other algorithms I've used in other packages.
If you go on YouTube, there's a woman from OptQuest, and she does a really great explanation of how it works. And she talks a lot about this issue.
Yeah, I will note that from the standpoint of publication, if you were to search on Google Scholar, OptQuest, there's scholarly papers to talk about its trade-offs, et cetera. Looks like there's about 2,000 references that come up. So it's a pretty well-used system. Now, there's some other mechanisms associated with this particular model that we've been running for sort of making these nice graphs and drawing these things and so on. But that's something that is less central. One of the things that is central, ladies and gentlemen, is that if you are running many replications with this, in other words, if you're running for each, remember my slide back there, if for each point in this space, remember it's searching around for the assumptions about the parameters that best match, that have the least discrepancy from the empirical data, or the model output, the empirical output of the model with respect to one or more time series, it exhibits the best match to the data. For each of those points, for fixed values of each of these, it's running it 5 times, or however many times you specify in this replications area, right? In this replications area. And then it averages the discrepancies between those, okay? So it takes the discrepancy, not the max, not the min, not the median, it actually averages them. And that is used to determine if this is the best discrepancy here, if it's the best one, okay? And you can actually ask here, what is the best one thus far, okay? So here, I believe, and there's a little bit of funkiness here, where it gets get the best parameter value, and this is asking the best value for this parameter, and it's a little bit of oddness where you have to kind of use this OptQuest variable contact rate. Anyway, you'll find videos of me talking about this in more detail, about how this works. I think there's even 2 video series of me talking about this. So calibration is a fairly important process for many empirically grounded models. I will say this, and I just want to note this. It's a very important consideration. This may look mechanical, and there are some pieces of it that are quite conceptual and quite mechanical as well. But what I will tell you is that there's a real art to calibrating. It happens to be an area where I've done quite a bit of specialized work, and I have some suggestions here in these slides about how to calibrate well. It's a great opportunity for learning, and you have to use it to that effect. You can't just sit back and say, oh, well, it didn't do that well, or oh, it went very well. You want to be able to use it to learn more effectively. And sometimes you see it getting stuck. It's not making progress, and it doesn't have a very good match. If it's not having a good match, you need to investigate why, just like you need to debug a program. You need to say, what is it that it's getting stuck about? That's where the learning really comes in. It's by trying to figure out why it's getting stuck. What is it about the data that is leading to it to have problems in optimizing? And this requires, just like debugging, running different tests. I want to test this, test this hypothesis, test this one. And trying it with other parameter values you think would be better than the current ones and seeing why those are worse. And you basically run it many times, and you're learning what is causing the problem. What is it about the model characteristics combined with the data characteristics that are really getting it stuck? And this is the opportunity to learn. Sometimes it may be the parameter space is too wide, but often it's something about the model that you didn't appreciate. That means if you match this time series, this one pops, like you squeeze a balloon, right? You squeeze it here, it pops out over there, vice versa. That's often what you learn from this, and that often gives you insights into, okay, is there something wrong with this data? Is there something wrong with this model? Could we change the model in this way? Why isn't this adding up? Do we really trust this data where it's matching on this particular data point? And so there's a whole process of setting weights that are different, trying out different parameter values to see why it's not working, trying out variations in the model, changing the number of parameters you're optimizing, examining changes to the model structure, disabling certain things in the model. That's how you get insight from this. And that's how you can use it, turn a model that isn't making progress in calibration from a perceived failure into a huge learning success. It's by exploring these things. And another one is this issue that Joe mentioned. Are the values unique? Are the values coming out of this calibration unique? Is it possible that maybe this is the seeming best one, but maybe there's 5 others almost as good with totally different parameter values? You can get a lot of insights out of this, and I actually built up some tools to provide some additional help with this. So I've given some suggestions here at a level of sort of thoughts about how you can work with it. Another thing is, if you find parameters that are it's the best, but when they're on the edge of the values you've permitted for them, that's often an issue. And you want to find out why. Why does it like that lower parameter value? How much further would it have to go to think it's, better? And so there's a whole set of experimentation here. But I've kept you long enough. I'll provide these slides to you. But calibration is something it's a real art. And I provided some suggestions, but I'm also happy to talk about it. Okay? It's a complex thing. I've talked to you about matching point-wise. Remember also, sometimes you just want to capture things in your calibration that are more rough, like that women should have a higher prevalence of gonorrhea in the model than men do. Or you want to capture that there are cycles in the outputs with respect to this time series, even though the exact timing of the cycles, the exact values of the maximum and minimums of the peaks are less important to you than just knowing there need to be cycles for it to match what people have reported to us about the system. So sometimes you're matching cycles, or that the fact that it should overshoot and collapse very quickly, or you're matching that this should be larger than that consistently. Don't minimize those things. Don't get caught up that it always has to be point-wise matches. because that is not always the salient facts that are known most keenly about the system. Sometimes it's these qualitative features about the system that actually are the ones known with great confidence. And the actual numeric values take back seat to those. Okay? So those are some comments about calibration. I'm happy to answer more questions about this, but I'm keeping you beyond time. So thank you very much for your time today. And we will talk about model conceptualization first thing tomorrow morning. Thank you very kindly. It's too kind. And I welcome again any comments about how we could make the materials online of better support for you. Okay?
That was a boxing kangaroo.
Was there a boxing kangaroo there?
You hit the thing. I didn't know what was going on there. It was with a marsupial.
Really? Oh, that would be really interesting. What was it? Did it come up for a second? Or?
You guys might pick up a virus.
Oh, this thing?
Yeah.
Oh, yeah. Well, if it's a boxing kangaroo, it's one that is native to Canada as well. I'm known to be emphatic with respect to the screen.
We need to jump as well at the same time.
Okay, that's good. So in my talk last week at this time, the photographer got very excited because he said I went airborne several times in my talk.
Does this support dimension classroom methods like instructor point analysis?
So that's a very good question. There's no built-in support for PCA or ICA or other things like that. So it's interesting. I was just talking with a researcher who specializes or is very interested in this issue of dimensionality reduction.